Hey gang, welcome to CSC470 Computer Graphics. Today we're going to, where are we and where were we? We started earlier talking about display systems, display technology, resolutions, things like that. Eric's been trying to sell me on 144 frames a second as the new must-have, which is interesting because I was listening to a podcast this morning, Eric, that had absolutely nothing to do with computer graphics. It's the Cool's World podcast that has to do with astronomy and physics and the search for exoplanets and exomoons. But anyway, the physicist there said something, and I have to look this up, but said something about the human eye could detect about 70 frames a second. So I was like, I've got to mention that to Eric with his 144 frames a second. So I need to go and I need to look to see deeper whether that physicist was just speaking off the cuff. But he's a fairly well noted physicist. And Zach's saying, I'm pretty sure that's wrong. It might be. I need to do some more research, but it just, I wasn't even thinking about computer graphics, but when he said 70 frames a second, I said, I got to mention that to Eric. And it's 144 frames a second. So something else for us to look at. So anyway, we were talking about that. Then we started talking about how polygons are saved, or actually how objects are saved. Objects are collections of polygons, and polygons are defined as ordered lists of vertices where you draw edges between them. And then ultimately you get down to the vertex list. We then talked about projection, right, which is how we take three-dimensional objects and we put them on a flat screen. Then we talked about, but the projection equations assume that the okay, somebody needs to mute. That your vertices are in the middle of the screen. That your origin is in the middle of the screen, and you're really looking, the screen is the XY plane, but really graphics hardware is built with the different, normally with the origin in the upper left-hand corner, and increasing Y goes down rather than up. So you have to use a little bit of math to flip someone goes and pushes your quadrant 1 over, so you have to do a little bit of math for that. So that was everything we needed to define objects and to get them on the screen. Where we ended up last time is we started talking about transformations, the 3 kinds of transformations that we have, which are translation, which means to move, scaling, which means to change size, and then rotation. And we had gone through, for 2 dimensions at least, we had gone through translation and scaling. Okay. So that's sort of where we are. Before this quarter's out, we're going to solve that question about whether 144 frames per second is bogus or whether or not you can actually see something. I would be interested in you guys talking to some psychology student because they always have to run experiments, right, into running an experiment to see whether or not people can actually determine the difference between, say, 30 frames a second, 60 frames a second, and 144 frames a second. I would be fascinated to see if the average person could. Andrew's wife is a psychologist, so that would be interesting. She's a psychologist, or she's a psychology student? Because that would be interesting. I didn't expect she would know, Andrew, but what I was saying is that that's the kind of experiment. It'd be easy to run, it doesn't hurt anybody, and it would come up with an interesting answer that's probably publishable. Okay, so let's go ahead and share our screen. So as I was saying, we've been talking about two-dimensional transformations. We've been talking about translation, scaling, and rotation. We're going to cover these things in 2D, and then we'll move to 3D, but quite honestly, the 3D is very close to the 2D. So translation means to move. Scale obviously means to change the size. We also have rotation. Now, we did talk about the fact that scaling and rotation are position dependent, while translation is not. In other words, if you move an object, a polygon, over 5 and up 6, it doesn't matter where it starts from, it's going to move over 5 and up 6. But if you do scaling, if the object is not centered on the origin, it'll scale, it'll change size, but it'll also move. And we looked at that. So for 2D scaling, 2D translation, we had these two equations. Your x translated is equal to your original x plus your translation factor in x. For y translated, it's your original y plus the translation factor in y. For these translation factors, if they're positive, they increase the size of the object. If they're negative, they let me back up here because it's early. If the translation factors are positive, this is translation, it will move the object to the right, okay, in X. If Y translation is positive, it will shift the object up. If these are negative, a negative X translation will shift the object to the left, and a negative translation factor in Y would move the object down. So for example, here is an original polygon, right, a triangle, and we are going to translate it in X1 and in Y2. So we're going to move it over 1 in X and up 2 in Y. And so essentially, you know, the base was at 1, 1. Well, now it's at 2, 3 because you moved it up 1 you moved it over 1 and up 2. So 1 plus 1 is 2, and 1 plus 2 is 3, and that's how this point becomes that. And normally, I mean, we applied these equations to individual vertices, to individual points, but really talking about, you know, rotation and scaling especially, it doesn't really make sense unless you're talking about an entire object that's composed of multiple points. So it's not like, here's what I'm trying to get at, it's not like you do these two equations one time for an object. You have to do these equations for every vertex in that object, if that makes sense. And here, again, we're showing moving this triangle over 1 and up 2, so I have to apply it to all 3 of the vertices to get the 3 translated vertices. And you'll remember when we were going over these, we said it's important to remember that these transformations are linear and that straight lines get translated to straight lines. So I want to move this whole triangle, but I don't have to examine every single point of the lines of the triangle. I can just move the 3 vertices and then just draw lines between the vertices like I had done originally, and the whole thing gets moved. So you really only have to worry about the vertices when you are applying the translation, scaling, or rotation. So anyway, that was a translation scaling. The equations are very similar. Really the only difference is you have a scale factor instead of a translation factor in X and Y, and you are multiplying rather than adding. So that's the only difference. In translation, you're adding by a translation factor. In scaling, you're multiplying by a scaling factor. So if the scale factor is greater than 1, you increase an object, you increase it in the x dimension if we're talking about sx, you decrease it in the y dimension, the vertical dimension if you're talking about sy. If the scale factor is less than 1, it's going to shrink the size of the object. Normally, sx and sy are the same value, like I'm going to make it a 2, so I'm going to double the size of the object, or I'm going to make it a 0.5, so I'm going to shrink the size of the object in half. But as we said, they don't have to be. They could be different, so you could squeeze in one direction, stretch in another. The most interesting thing about this, though, or the most unexpected is, again, if your object is not centered on the origin. So this triangle is not centered on the origin. So because of that, when you scale, the object shifts. It translates as well as scaling. So, so you need to keep that in mind. And again, normally you're doing multiple points. They're normally the vertices of an object. And I grind through the math there so you can see exactly how these points get changed to these other points. So for example, you can see how 1, 1 gets placed at 1.5, 1.5 through these equations here. And you can see how 2, 2 gets moved to 3, 3 from these equations here, and how 3, 1 gets translated to 4.51 by these equations here. So if you're not 100% on the math, I'm giving you examples that I worked through so that there should be no gaps here. I go through in excruciating detail with examples, so you should be able to see. The second example makes 2 points. One is it shows what happens if your object is centered on the origin. Our object is this blue thing here. I don't know what you want to call it, a diamond maybe, I don't know. And we're going to shrink it. We're going to use a scale factor in both x and y of 0.5. And when we do that, you see that the center of it doesn't move. The center of the bigger blue original object is the origin, and the center of the new, smaller, computed dashed green object is still the origin. So if an object is centered on the origin and you scale it, it does not move. Its visual center stays in the same location. If it is not centered on the origin and you scale it, it'll scale. It'll get bigger or smaller depending on how you scaled it, but it will move. If you are scaling it larger, it'll move away from the origin, and if you're scaling it smaller, it will move closer to the origin. And that's interesting because if you set your scale factor all the way to 0, basically the object implodes into the origin. Everything becomes 0. And so it's like the object falls into a black hole that vanishes to a point. If your scaling factor is 1, the object's unchanged. And like I said, if it's 2, it doubles. If it's 0.5, it shrinks in half. Oh, and scale factors, unlike translation factors, are generally assumed to be positive. You don't ever have a negative scale factor. Okay? Are there any questions? This is basically a recap of where we've gotten to so far. Any questions? No questions. Okay, so today what we're going to do is we're going to talk about rotation. So rotation is rotation through some angle. We usually, in my notes, will use phi, this little symbol here, pronounced phi, to specify the angle that we're rotating through. And rotations in 2 dimensions happen in a counterclockwise direction. You rotate from positive x to positive y. So it's counterclockwise again because if you think about our coordinate system, right, where this is positive x and this is positive y, we are going to rotate counterclockwise. So if I've got an object here, point, I'm going to be rotating it through some angle. My hands are vanishing. Through some angle, right, going in this direction, in the counterclockwise direction. So it's from positive x to positive y. So if your object, rotation is position dependent, just like scaling was. So if the visual center of your object is located at the origin, the object will appear to rotate in place about that visual center. If your object's center is in the middle, is at the origin, then the object will appear to rotate in place. If the visual center of the object is not on the origin, the object will still rotate about the origin. It will appear to rotate through an arc in a counterclockwise direction. Now, I put visual center in quotes because a lot of times students say, well, what is the visual center? It is not a precisely defined term. It's not like center of mass or something like that. It is where a human looking at it would say, this is the center of this thing. It's generally towards the middle of the object. So that's about the best I can say. It's like, okay, well, what would you say is the center of the object, right? And that could differ, but it's basically, it's sometimes where the center of mass would be, but it doesn't have to be where the center of mass would be. You know, if you imagine a rotating wheel in space, or even a rotating wheel on a car, the visual center is where the axle would be, right? And that's also pretty much the center of mass of the tire, if you're thinking of it like that. But we could imagine something else where you've got, say, I don't know if you guys did this when you were kids, but we did it when I was a kid. You take a bucket, you put water in it, you put a rope, have a rope tied to the handle of the bucket, and you could find that you could spin around and swing the bucket, right, and the water would stay in the bucket. It's how children discover a centrifugal force, right? It's like, wow, the water stays in the bucket. You've just learned physics. In that case, right, the most of the mass, if you take out the fact that I'm a person and I weigh a lot, right? If you just consider that as a point that the bucket is spinning around, well, most of the mass is in the bucket, right? But it's still, you would expect it having some point for it to be spinning around this point here. But if you were to draw it like with a point and a line and then a bucket, right? You know, the center would be like, you might argue it's there, or you might argue it's in the bucket, but really the center of that diagram is actually the point at the end of the rope where the human is standing. And that's what you would expect it to rotate around, and it does. So I'm just trying to say that don't think that the visual center is some particular point. Andrew is saying, would it be the average of all of the vertices? That's a good first approximation for most things, Andrew, but it's not a guarantee. If we were doing a pyramid, right? A pyramid. Think about the pyramid that we defined. Think about the pyramid we defined. I'm going to go back and I'm going to show that pyramid again for a moment here. All the way back in time in our Wayback Machine. Well, there are 5 vertices. If you were to average, let's call this dimension the y dimension, the height dimension. If you were to average them, the center would be much closer to the base than we would say it is, because this is the only one that's got that's up at the top, right? And the 4 base ones are at the bottom. So if you just average the vertices, you might think the center's here, but really the center's more like here, the visual center. So there's no formula, there's no exact formula, there's no exact definition for what's the visual center, right? A lot of times what you can do, and let's see, Eric is saying this, is that, I think he's saying this, let me look and see exactly what he said. Take the center of each of the dimensions. So one thing, that's a better approximation than what Andrew was suggesting, Eric, which is create a bounding box around the object and take the center of that bounding box, which is what you would get if you did what you suggested here, take 0.5 of each of the sides. And so that would give you the center about here. Well, actually, right, it's moved inward. I'm showing it on the front face, but it's, right, that would give you the center. So if you took this dimension and this dimension, right, and the z dimension, and drew a box around this thing, took the average of that box, the center point of that box, that would give you the visual center of this pyramid. And frequently, that's what we do, but it's not necessarily always going to give you the result that every human would agree is the center. Okay, so there's not a perfect definition. It's what looks to be the center. But bounding box, center of a bounding box is probably the best you can do computationally to sort of guess where the center, where a human would say the center probably is. Okay. All right. So we've covered that. So what are the equations for this? Well, x rotated is equal to x times the sine of the angle, the cosine of the angle, minus y times the sine of the angle. And y rotated is x times the sine of the angle plus y times the cosine of the angle. Where did those come from? I've forgotten all of my trig. Let's crawl through this, okay? And because my memory is bad and it's hard for me to remember math, let's start at the most basic. What is sine and what is cosine? Well, you know, it's this periodic wave. There's the sine wave and the cosine wave. And really, they're exactly the same wave that is moving from 1 to -1 and back again, right, over a period here, right, in a period of 2 pi, right? So if you look at cosine here at negative pi, it's at -1, and then at 0, it's at positive 1, and then at pi, it goes back to -1. So in a period of 2 pi, it goes from -1 to 1 back to -1. Sine is the same wave. It's got the same periodicity. It's got the same magnitude. It's just that sine is shifted from cosine by 90 degrees. So when sine is, so it's shifted by 90 degrees here. So if you were to look at, say, 90 degrees, cosine is halfway through its period, so it's at 0, while sine is at its height, so it's at 1, right? So at 90 degrees, the cosine is 0 and the sine is 1. If you go another 90 degrees, right, the sine will be at 0 and the cosine will be at -1. If you go another 90 degrees, the cosine will be at 0 and the sine will be at -1. If you go another 90 degrees, you'll be back where you started with the sine at 0 and the cosine at 1. And so you still have, they're the same thing. They both have the same magnitude, right? They both have the same periodicity. You might say, 2 pi sounds familiar. Well, right, it's based on a circle, right? So those are our sine and cosine basic definitions in terms of a wave function. You can also define them in terms of trigonometric functions, which we'll see in a minute. But that's the basic definition. And also, there are two separate systems for talking about these things. I've been talking in degrees, right? 0, 9 degrees, 180, 270, 360. So a circle has 360 degrees in it, right? That's also the same thing as 2 pi. When you're talking in terms of this top bar, you're talking in terms of radians. And again, it's just two different systems. We're going to use degrees. Most of the internal math packages use radians, but there's a function to convert from degrees to radians. So if my input was 5 degrees, you would take that, convert it to radians, and then probably feed it into your trigonometric function, because your trigonometric function is expecting radians. Okay. So, you've given me these formulas, Mike. You've at least explained to me again, reminded me what sine and cosine are, and looking at this little table, I can compute some basic values, like what's cosine going to be at 0, what is sine going to be at 0, and what are they going to be at 90 degrees, etc., the main lines here. So let's say that we want to do a counterclockwise rotation of 90 degrees from positive x to positive y. So if I'm going to do a 90-degree rotation, 90 is going to be my phi. So mathematically, if it was in a program, you'd have to convert that 90 degrees using a built-in function to convert it to radians. But either it's pi over 2 or it's 90 degrees. Either way, the sine of that's 1 and the cosine of that is 0. The sine is 1, the cosine is 0. So we can take that and we can plug it into these equations here. And in this particular case, what happens is for this particular case, the equation simplifies. So cosine of phi is 0. So in this case, the x component goes away. The cosine of 90 degrees is 0, so the x goes away when you're computing x rotated. And since sine of phi is, or sine of 90 degrees is 1, you get x times 0 minus y times 1. So in this case, x rotated is just minus y. And y rotated is also, in this case, because our angle is 90 degrees, you see that this becomes x times 1 plus y times 0. So the y goes away. And so y rotated is just x. So what happens is basically your x and your y swap, and your y gets a negative put in front of it. In this particular case, the x and the y swap. What was x becomes y, and what was y becomes x, but you have to remember to negate the y. So 0, 2 will become minus 2, 0, right? Because again, the y gets negated, right? 4, 0 becomes 0, 4. Well, you're negating 0, and that's just still 0. 0 minus 2 becomes 2, 0. And minus 4, 0 becomes 0 minus 4. And you can see here's our original object in blue. It is centered visually on the origin. And here is the resulting object after the rotation. And you can see I have taken this thing and I have rotated it 90 degrees counterclockwise. This point here moves 90 degrees counterclockwise to here. And this -2 moves 90 degrees counterclockwise to here. And this -4 moves 90 degrees counterclockwise to here. And this 4 moves 90 degrees counterclockwise to here. So when you move all the points and you redraw the lines, this thing that was longer in the horizontal angle has become longer in the vertical angle, because you just took this thing and you just went rotate it counterclockwise. If it were a clock, from the 3 o'clock position to the 12 o'clock position, that's what you did. Does that make sense? Do you see the math? Do you see the points? Do you see how the points were translated? Are there any questions? Any questions for Mikey about this? No questions for the Mikester. Okay. So, let's look at one more example. Let's say that we want to do a 45-degree counterclockwise rotation. 45-degree counterclockwise rotation. So what's that going to be? Well, if we go back and we look, here's 0 degrees, here's 90 degrees, so 45 degrees is right in the middle. And lo and behold, at 45 degrees, cosine and sine cross. So at 45 degrees, they have exactly the same value. And you look over here on the scale, this is 1 and this is 0.5. It crossed here. They cross at about 0.7. Okay? They cross at about 0.7. And so, if we go here to 45 degrees, the actual value is 0.707. And it's actually the square root of 2 over 2, so this is my fraction, is just an approximation. But if visually what we're trying to do here is we're trying to take our same original blue little, whatever you want to call it, diamond, at the same original point, and we want to move it not 90 degrees, we want to shift it 45 degrees. And this is about as close as I was able to get to draw the thing. I'm no artist, but this is about a 45 degree shift here. Okay. Looking at the equations, cosine of 45 degrees and sine of 45 degrees, they're both 0.707. So you can see it's x rotated is x times 0.707 minus y times 0.707. Or you could simply say x minus y times 0.707, and y rotate is the same sort of thing, only instead of a minus, you've got a plus, so it's x plus y times 0.707. And so you can see that 0.02 over 0 up 2 gets converted to minus 1.4, 1.4. So this is 2 here, so I need to go over about 3/4, right? 1.4, and then up 1.4. And so that's how this 2 shifts to here, right? And 4 over up 0, that's going to become 2.8, 2.8. So again, that's about here, okay? And again, you should follow each of those points. Do you have any questions for me? Both of these, I was using the same original object that was centered on the origin, so this appears to be a rotation in place. Note that if I had done a third example where I had an object that was not centered on the origin, it wouldn't rotate in place about itself, it would still rotate about the origin. So if I had think about it like this. This is point what? 40, right? Over 4 up 0. What if we had taken this object, this whole object, and we had shifted it over 4? okay? Or let's say we shifted it over 8 to the left. So this point would now be right here. See that? If I took this whole object and I shifted it over by 8, this point that's at -4 would now, at -40 would now be at 40. So in your mind, think about taking this whole blue object and shifting it over so it's here, right? It's here. It starts at 4 and it ends at 8. This point, since it's 40, points are rotated independently, so it's still going to end up here at 0, 2. But the object would be up here, right? Because this is now this anchor point here that got shifted over, so it would be this whole thing, right? It would, if we were doing it by 90 degrees, it would be this whole thing. Maybe I should shift back to the 90-degree one so it's a little easier to see. So if I were rotating counterclockwise by 90 degrees, but I had shifted this blue thing over by 8, this point here would now correspond to this leftmost point on the object. That leftmost point will still end up being the bottom point, right? But it will be here, and so the object would now be up here. So the object still went through a counterclockwise rotation of 90 degrees, but it did so still about the origin. If you're just thinking of it of itself, it will move, right? It will still rotate around the center point. It won't rotate. It won't do a rotation in place. It won't end up here, right? It's going to end up over here because it's still rotating about the origin. Does that make sense? If you're having problems seeing that, what you need to do is you need to go and, using these equations, create on your own a third example with the new points, right? Where you take this shape and you plot it over here, right? Where, again, -40 is going to be 40, and 40 is going to be 80, right? So plot the thing over here and then plug the values through the equations, and you'll see it'll end up being rotated, but it'll end up over here in this region. Okay? Questions for me? Okay. Okay, Mike. I followed your examples. I'm starting to remember a little bit about, sine, cosine, and this other thing. I think it's called tangent. And yeah, I understand. It's the sine wave, the periodicity of the wave, the fact that cosine and sine are simply out of phase by 90 degrees. Yeah, I'm beginning to remember all of that. I see the math. I see how, from these two examples, that they do perform the rotation. And yeah, I need to work that example that you mentioned, but I see that if the object visually wasn't centered on the origin, that it would still rotate about the origin, so it wouldn't be a, quote, in-place rotation. I see what you're saying and all of that. But dude, where do these formulas come from? Did you just pull them out of the air? Can you give me some insight into how these equations work? And Mike says, I'll be happy to. So let's look at how we derive the rotation formulas. So these rotation formulas can be derived from some geometry, some basic trigonometry, a little bit of algebra. So they're really pretty basic. Now, we can simplify matters a little bit by saying, okay, let me try something here. Oh, yeah, look, that draws. I don't know how to get rid of it, but I can draw. That's good to know. But like I said, now I need to figure out how to get rid of it. Well, I did something there. Does that work? Nope. This is great. I figured out how to make marks on the screen, but I hadn't with my ink pen, my electronic pen, but I hadn't figured out how to erase anything. This is why you shouldn't play with this. Oh, maybe that's how you work with mine. Yeah. Okay, so this is going to make things a little easier, I think. So here you can see that it was a 45-degree counterclockwise rotation. We're supposed to erase it because I hit the little button. Okay. Okay. We want to take a point, okay, P. We want to take a point P that has a value of X and Y. So here's our axis. Here's our origin of 0, right? 0, 0. And here's the x-axis. This is positive X. Here's the y-axis. Is positive Y. So for my point, and right now we're ignoring all the light blue. We're just looking at the black marking. I can talk about point. What does it mean for point P to be at X, Y? Well, it means that it's off-shifted some distance in X, right? That's the over. And I've got the X drawn up here, but I can just as easily draw it down here. In fact, X is labeled ON. The line segment from O to N is exactly X. These two lines are parallel and have exactly the same length. So X is really ON. Y is the other component of this point. It's the height. It's the displacement in Y. Okay? So the displacement in X, the displacement in Y. Okay? Over X, up Y, takes me to point P. And we could draw a line from the origin to P, and this would be the line OP. Now, we noticed that if you look at ONP, you've got a right triangle, right? With basically the base is X, or ON, the height is Y, and the hypotenuse is this line OP here. And we basically remember something about X squared plus Y squared equals Z squared, right? So the length of this line is the square root of X squared plus Y squared. Yeah, I remember that, the Pythagorean theorem, right? Okay. Now, what we're going to do is we're going to make a little observation. And the observation is that if I want to rotate this thing counterclockwise by some angle, I want to rotate this counterclockwise by some angle. Okay. I'm rotating it by some angle phi. Okay. Instead of doing that, I could take instead of rotating this point by a counterclockwise of the angle phi, I could take the whole friggin' reference system and I could rotate it by the same phi, but I could do that counterclockwise. So one way of looking at things is rather than rotating the point counterclockwise by phi, you can rotate the reference system by phi. And that's what we're doing here. We're rotating the reference system by the angle phi. And here you can see phi, here you can see our little angle. Okay? And what we're doing is we're taking our reference system and we are shifting it. So with with Mr. Hand, right, I'm taking, if you'll stay visible, I'm taking my reference system and I'm shifting it like this. Why does my hand keep vanishing? Taking my hand and I'm shifting the reference, the coordinate system. There should be a trash icon that lets me clear everything. Well, I'll keep my eye open for it. Okay, so does everybody see what I'm going to do here? Okay. Doesn't like Mr. Hand, clear, John. Does that make sense? Do you see what I'm doing? I am taking the system and I am moving it clockwise by the angle phi. So now if I do that, my x-axis and my y-axis is shifted through this angle and my x-axis is shifted through this angle. I'm showing y prime and x prime as the new axes. This is just the reference, the coordinate system having been shifted phi clockwise. Okay? So now in blue, I'm drawing another set of triangles. If I look at this point, it's now in the new coordinate system, it's x prime, y prime. It's the same point, but it's in a new coordinate system, so it's going to be called x, y, y prime, x prime, y prime. And so what's the distance from O to N prime? Well, that's the distance in x prime. So this distance from here to here is my x in the prime coordinate system. And the distance from here to P is y prime. It's my distance in the new coordinate system in y. So you might notice I've got another right triangle here, right? So O in prime, that distance, which is x prime, right? So x prime squared plus y prime squared equals OP, the length of OP, okay? Well, squared. So the square root of x prime squared plus y prime squared is going to be the same distance. And this distance didn't change. That line didn't move, right, between the two coordinate systems. So now, with a little bit of math, we will be in trig, and now that we've gone through the geometry, we'll be able to derive these equations. So the first thing we would need to do is we need to think about a sine and cosine again in terms of the ratio of the sides of a right triangle. We've already reminded ourselves about sine and cosine as a wave with a particular wavelength and a particular periodicity, right? But we can also define sine and cosine in terms of a right triangle. And so sine is remember it's a right triangle, so you've got the base, you've got or if this is the angle, that base is the adjacent. You've got some height, which is the opposite side from the angle, and then it's a right triangle, so this is the hypotenuse of these two. So sine is just simply defined as the opposite over the hypotenuse, while cosine is defined as the adjacent over the hypotenuse. And that's definitions for sine and cosine from your first day of trig. Okay. Now here's something, we're just going to accept this on faith because we learned it when we took our trig class back in junior high or high school or whenever we first took it. And quite frankly, I've forgotten why this is true. I'm sure I could sit down for 20 minutes and convince myself it's true because it's coming from, this situation where we have two angles and we want to add them together and figure out the sine and the cosine of that composite angle given the sine and cosines of the original angle. So somebody long ago worked out that these statements were true. Okay, so the cosine of two angles, alpha plus phi, is the cosine of alpha times the cosine of phi minus the sine of alpha times the sine of phi. And the sine of alpha plus phi is the sine of alpha times the cosine of phi plus the cosine of alpha times the sine of phi. What is this angle alpha? It's just this it's this angle that our first right triangle in our base coordinate system was based on, okay? And again, phi is this angle that we are moving our coordinate system through. So we're going to be interested in the cosine and sine of this angle here, which is alpha plus theta, plus alpha plus phi. Does that make sense? Right? So that's what the alpha is. The alpha in this case, these rules work for any two angles that you're adding together. I'm using phi because that's the angle that we moved our coordinate system through, and alpha is the original angle that existed for this right triangle before we moved our coordinate system. Okay. Now, let's see if we can figure out what's going on here. I'm going to split my screen here to make things a little easier. Let's see. So, to begin with, I'll make them go away. So, to begin with, I'm just going to repeat what we had on the previous page, which is these two rules for cosine and sine, and what are the reasons for these equations? Well, they come from trigonometry. The next thing I'm going to want to do is I'm going to want to say, okay, we said this before, but x is equal to ON, right? This length is equal to this length. They're the same, okay? Reason, C diagram. Now, if I wanted to, and you might say, Michael, why would you want to? I could both multiply and divide this term by OP. OP, this thing here. Why can you do that, Mike? Well, because OP divided by OP is 1. It doesn't matter what the OP is. And you can always take a value and multiply it by 1, and you don't change the value. So you might question my sanity for doing this, but you would never argue that I had done something illegal. So x equals ON, and if you want to, you might, I don't know why you would want to, but you could rephrase that as OP times ON divided by OP. Because all you did there is you multiply the value by another name for 1. Does everybody agree with that? Okay. You might be crazy for doing it, Mike, but I'm going to allow you to do it. Well, in the next step, you see, no, Mike isn't crazy. Well, maybe Mike is crazy, but he had a reason for doing this because what is the definition of cosine of an angle? Well, the definition of the cosine of the angle is the adjacent over the hypotenuse. The cosine of alpha is the adjacent, right, which is ON, over the hypotenuse, which is OP. So x, which equals ON, which equals OP times ON over OP, you can take the ON over OP and you can replace that with sine of alpha, with cosine of alpha, because that's what it means. So x is actually OP times cosine alpha. Do you see that? I didn't do any trickery. It was really very, very straightforward. Okay. I can do exactly the same kind of thing with y. What is y? Y is the height in this original axis system. What is y? Y is the distance from n to p or p to n. So y equals np. They're the same thing. Reason, see the diagram. Okay, again, you can say that Mike is crazy, but he could multiply NP times 1, where he casts 1 as OP over OP. And if you do that, you can see that you can rewrite NP as OP times NP over OP. All I did was multiply by 1. Okay. But there's a reason for the madness, because what is sine of an angle? It's the opposite over the hypotenuse. So are still working with little angle alpha. It's the opposite, which is NP over OP. So that's sine. So y can be written as OP times sine of alpha. Okay. Again, nothing hard here. We're just using just a little bit of trig and a little bit of algebra. Okay, now let's look at those two were for our original coordinate system. Let's do the same kind of thinking in our new coordinate system here. Well, what is x prime? What is x prime? Well, x prime is the same thing as O n prime, right? Why? See the diagram. It's very obvious. Okay. All right. Again, we can play our silly little game of taking that value and multiplying it times OP over OP, which is 1, right? And when we do that, right, we get that x prime, okay, is equal to OP times ON prime over OP. ON, right, is equal to OP times ON over OP. We just multiplied and divided by the same quantity. So what is ON prime over OP? Well, that is the adjacent over the hypotenuse. If you add both of these angles together, alpha and phi, right? So now we're talking about this combined angle here, right? What is the cosine of that combined angle? Well, the cosine of that combined angle is the adjacent ON prime over OP. So x prime is equal to OP times cosine of alpha plus phi. Now, if you go back to equation 1, we can replace cosine alpha plus phi with this little piece of beautifulness here, all right? That comes from our equation 1. Our equation 1, right? 1 and 2 there. Okay. All right. So now then you can just take, because this is a quantity minus a quantity, and you're multiplying OP by this combined thing here, well, you can break that down to be OP times cosine alpha times cosine phi minus OP times sine alpha times sine phi. Okay, well, that's interesting because equations 3 and equation 4 said that OP times cosine alpha was just x, and it said that OP times sine alpha was just y. So from equations 3 and 4, x prime equals x times the cosine of the angle phi minus y times the sine of the angle phi. And I wrote that in bold because, lo and behold, if I can stop making myself sick there, because lo and behold, that is the, we'll get to it. We'll get to it, Mikey. We'll get to it. That is that equation right here. So we've derived the x equation, okay? Well, what about the y equation? It's going to derive similarly. Scroll, 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 scroll. We're scrolling, we're scrolling, we're scrolling along. We're scrolling along, we're scrolling, we're scrolling, we're scrolling, we're scrolling, we're scrolling, we're stopping. Okay. So we got our x, let's do our y. It's exactly the same sort of thing. What is y prime? Y prime is n prime p. I can multiply it times OP and divide it by OP, and I get OP times n prime p over OP, but this is the opposite over the hypotenuse. For this combined angle, alpha plus phi, it's the opposite, all right? In this right triangle, it's the opposite over the hypotenuse, and that gives you sine of alpha plus phi, OP times sine of alpha plus phi. Well, we can use equation 2 and rewrite the sine of alpha plus phi as this. We can then multiply the OP times both components. We get this, and now we see the OP sine alpha from one of our equations, I think it was 3, is just y, and from 4, OP times cosine of alpha is just x, and now we have our final equation. Y prime equals y times cosine phi plus x times sine of phi. Okay. Why did I go through all of this? Not because I want you necessarily to have it all memorized so you could regurgitate it on exam. We're not having exams. I'm doing it because I wanted you to see that even though rotation, look, scaling was obvious. The formulas were intuitive. And translation, the formulas were obvious. They were intuitive. These two things are not intuitive. So I wanted us to go back to the definition of sine and cosine, both in its wave form and in its triangular form. And I wanted us to first know that the equations work by looking at a couple of examples. And then I wanted us to answer, okay, where did these equations come from? So we went through this again. I'm not expecting you to memorize it or anything, but I wanted to show you that it really isn't, there's nothing really complicated. If Mike O'Neill can remember or can walk through the math for this thing, it's really straightforward. It's just a little bit of algebra, a little bit of trigonometry, a little bit of geometry, and a little bit of time to figure it out. The only step that you probably don't remember is this, and we're just accepting that. If we want to look into why, I'm sure that I could prove that that's true by looking at the triangles, okay? So the point is that while rotation isn't as intuitive as the other transformation, it's not that difficult, really. A little bit of thought and spend a little bit of time, and you can see exactly where it comes from. So what have we done now? We've now covered in the 2D case translation, scaling, and rotation. And I have pointed out that scaling and rotation are position dependent. If the visual center of the object isn't the origin, things are going to, still scale, but they're going to move. They're going to translate, and things will still rotate, but they'll also translate. So where are we now? Well, now we're pretty much ready to mention the three-dimensional versions of these transformations. We're going to go back and we're going to spend more time on the 3D, but I want you guys to get started if you haven't already done so on assignment. And so here are the 3D transformation. And if you look at translation, there's only one new formula. So you still have X translated, you still have Y translated, but now you have Z translated as well. And it's exactly the same. So instead of just X and Y, you have X, Y, Z. Instead of just a translation factor in X and translation factor in Y, you still have your X and Y translation factors. You now have a Z translation factor too, because you've got another axis, right? So this is all you need to know about 3D translation. It's just like what we talked about in 2D, except now you also have the Z axis that you can translate now. About scaling. Scaling is exactly the same. The only difference is that you have one more equation where you can scale in Z. All right. So it's the same thing. It's just that you can now no longer just scale in X and just scale in Y. You can also scale in Z. So there's very little that you have to worry about for 3D translation and 3D scaling from what we already talked about. Now, rotation's a little more, okay, because rotation is defined about within a plane or about an axis. So what we've already covered, 2D rotation, this was 2D rotation. Well, if it's in 3D, you have to add Z rotated is just Z. So what we've done is we've rotated, the rotation that we covered was a rotation really within the XY plane where we weren't changing the Z values. If you want to be able to do 3D rotations, you have to do the other two parts of it. So this is rotation within the, again, what we originally did was within the XY plane. You also need to do rotation around the Y-axis, which is rotating within the XZ plane. Y stays the same. And you also have to do rotation about the X-axis, which is rotation in the ZY plane. And here are the formulas for that. So instead of just adding an extra formula, you have now 3 sets of formulas where before you only had 1 set of formulas. So again, what is happening here? Well, originally we did rotation, counterclockwise rotation. And if you think about 2D, well, you have an X and you have Y. But if you think about 3D, you also have a Z, right? A Z. Well, in the first thing that we did rotation within the XY plane. So it's like you're looking directly at it. You also have to be able to do rotation when you're looking down, when you're looking from the Y-axis. So here, you're looking at the Y-axis down to the XZ plane. So that's that second set of coordinates. You also have to be able to do the side where you're looking, actually it's this direction from you guys' point of view, from positive X here, and this is the YZ plane. So there are 3 planes in which you need to be able to rotate. That's why there are 3 sets of equations. Okay? Questions for me there? Andrew, we have not actually talked about vector manipulation yet, so you should use these equations as I've given them to you. Okay? We will be talking about vectors, but that'll be shortly after we get back from Christmas. Do you use a standard for rotation in each plane? If you look at what I presented to you, you see that we always go from a positive to a positive, right? From positive X to positive Z when looking from positive Y, from positive Z to positive Y when looking in positive X. The only anomaly is because we're using a left-handed system, we're actually in negative Z. So we look actually from the negative Z position towards the screen. If we were in a right-hand side position, this would be the opposite, okay? Why don't you, well, normally what I'm going to ask you to do, Andrew, look at the programming assignment, and that'll answer your question. We're going to talk about the programming assignment next time, but I will typically say I want you to rotate this object by so many degrees in the counterclockwise direction along the x-axis or along the y-axis or along. I will give you the axis and I will give you the angle to rotate through. There is no theta. I don't know where you're coming up with that. At one time I accidentally called phi theta, and I don't know where you're coming up with this. I haven't said anything about that. All we've talked about is the angle phi. I introduced the angle alpha to help us derive the equations, but it doesn't show up in the final equations at all. Okay, so you're throwing out Greek letters that we haven't assigned anything, man. So I have no idea what you're doing there. Okay. What are we going to do next time? Next time we are going to next time we're going to look at. I'm going to go through the programming assignment carefully with you, line by line. I'm going to show you the program running and the interface that I've built for it, and then I'm going to go through the code of a framework for the program that implements fully the interface. So you're not going to have to worry about how to put buttons on screens and all this stuff. I've forgotten all that, Michael. You're not going to have to worry about that. I'm giving you all of that, and basically it'll be that template that you'll use to fill in the equations to build the assignment. If we finish early, which could happen depending on how many questions you have, I'll let you guys use the rest of your time for your team meetings, because remember I stole Friday from you, and you guys will be getting ready for your presentations that'll be on this upcoming Friday. I expect you guys will probably have questions for me on Wednesday about what I'm expecting in those presentations, and I'll be happy to answer them. But anyway, I see I'm 2 minutes over time, so I'm going to call it quits here and end the recording. For those of you who want to stick around and ask me questions, I'll be happy to answer them. Otherwise, until next time, friends, be seeing you.